Very warm and exciting good evening to all my dear friends, my dear students, and my well wishers. Once again, I am right in front of you with a very interesting area of the physical chemistry, that is the thermodynamics. As far as thermodynamics is considered, it comes both in the physics as well as in the chemistry. It is considered to be the toughest area. It is so because of the lack of the proper mathematical understanding, proper knowledge of the calculus, and proper understanding about the thermodynamic parameter, the thermodynamic fundamentals, and thermodynamic potentials. Exactly, entire thermodynamics is based on three very vital and important pillars. Number one is the basic parameters, also called thermodynamic variables. Second one is the fundamental properties of the thermodynamics, which straight away come from the thermodynamic laws, like here the first law and the second law. From the first law we obtain the concept of internal energy. From the second law we come to understand about the entropy of the systems. Similarly, the third one is the thermodynamic potentials, or also called as here the energy potentials, in which we cover all the energy potentials used in the thermodynamics, like here the internal energy, enthalpies, Gibbs energy function, as well as the Helmholtz energy functions. All these variables, with the help of the fundamental laws, are associated with the energy potentials, and most often when the questions in the examinations appear from the thermodynamics at the higher level of entrance examinations, the very look of the question itself is horrifying. There are innumerable, uncountable type of the equations, innumerable number of the formulas in the thermodynamics. It becomes quite imperative to make you learn all these formulas in the shortest possible of time. Exactly today, I'm just delivering the lecture only on exactly how in the thermodynamics you have to advance your studies in details. From the next class onward, I'll be taking individual areas. This is going to be the longest series in the physical chemistry because the areas are very vital, very important. Even this year in the JEE advanced examinations, the questions that have been asked from the thermodynamic areas were not a very simple questions, were not only confined to the knowledge of the NCERT levels. You need to understand thermodynamics much beyond the scope of the NCERTs. Today I am going to explain to you a magic square. What exactly is the magic square? It is simply nothing but a way to remember, way to learn the various relations, various equations, thermodynamic equations of state. Just as in case of the physics, you apply that delta U is equal to NCB delta T. Delta H is equal to NCP delta T. In physics, you do not bother about whether you are applying this for any process, because in physics you deal only with the ideal gas. And for ideal gas, for all process, even for solid, liquid, gas, without any hesitation, you simply implement the equation delta U is equal to NCB delta T. But exactly when the same equation is to be applied in case of the real gases or the van der Waals gases, then exactly you need to understand the thermodynamics beyond what exactly you know from the physics. So today I am just for a glimpse, I have just presented two very prominent questions asked in the past in the IT examinations. The very look of the question is slightly offending to most of the students. If they look at these questions, they will find that they haven't gone through this type of relations in any part of the thermodynamics, in any area of the NCRT, in any area of the text that you study. But these are the questions that have been asked in the IT examination because they want you to understand the perspective of the theoretical knowledge that you have gained, how you are going to implement that on the logical and the practical ground. Let me get back to the board and just get you introduced with the horrible looking kind of the questions and how exactly you have to give the answer of these type of the questions without wasting any time in a time frame of the 30 seconds. But for that you need to understand, because I am not today starting thermodynamics from a very introductory part. I'll be starting from the next class onward, which will be beneficial to students of all sections, all classes. This lecture is especially designed for the students, those who are going to appear for the IT advanced examination in the due course of time. Let me get back to the board and let us have a glimpse on the question that I have just presented on the board and how exactly we have to understand them. I will explain you the concept, and thereafter in a jiffy of time you will be able to find the answer of all these kind of the questions in no time. In no time I means in a time frame of the 30 second itself. Exactly what I am going to explain today is, this is the max bone yani magic square. Let us first have a look on the question that I have just presented on the board. The first question speaks out about which is incorrect out of the four options A, B, C and D. There are some differential relations just presented over here, and if you very honestly go through your knowledge, go through your study, you will be baffled by looking at these kind of questions, because these are the kind of the questions that you might have not encountered during your regular studies. The equations, it is temperature, it is the differentiations of the temperature with respect to the volume, keeping entropy as constant, is equal to the differential of P with respect to here, that is here S and entropy, keeping here this temperature to be the constant, keeping the volume to be constant, and this way there are the four options. Similar type of the question is which is or are correct. Again, these are the differential equations that have been presented, and accordingly you have to look upon them and have to find out the answers. Now the very big question arises that these are the kind of equations that we haven't gone through at all during our studies. How exactly we have to understand them, how we can find out the answer in a quicker time. Let me explain to you. Max Born scientist just presented a very important tricks to find answer of these type of the question in the shortest possible of time. He has presented here a magical square, a jadui dibba, or you can call it as a magic square, thermodynamic square, Max Born square. Exactly, we need to focus on exactly what this square represents and how you have to establish the relations out of this square. In this square, I have just made here a square. At the four corners of this square, I have represented S, P, V, and T. S is entropy, P is pressure, V is the volume, T is here the temperatures. These are here the these are here the basic parameters or the basic variables. Basic variables, I mean to say, you have to remember this way how you can, whatever technique you want to explore for yourself. What I have just made a trick to learn this, that is a sweet, as a stand for your sweet pastry, sweet pastry, very tasty, sweet pastry, very tasty and tasty. Here in this case, sweet stands for, sweet here stands for your S, pastry stands for your P, very stands for your V, and tasty here stands for your T. Remember the order, you have to go from left to right and then again from left to right. Left to right on the top of the square, left to right from the bottom of the square. These are here thermodynamic variables, and in between these variables I have written the energy potentials. These are the energy potential that we study in the thermodynamics. One is your H, second is your G, this is your A, and this is your U. You always start from your H to remember this kind of the mnemonics. That is your hey God. You can remember like this, hey God, all you. Hey God, all you in Hindi mean हे ईश्वर तुम्ही सब कुछ हो. हे यानी that is your H, that is enthalpy terms. God gives free energy. A is called as the Helmholtz energy, and you understand is the internal energies. These are called here, these SPVT, these are here the basic parameters or the basic thermodynamic and variables, and these are all energy potentials which are related with the energy of the thermodynamic system. How the variables are interrelated, how these energy potential are interrelated, how exactly they are mutually related, there could be various and a number of expressions which can be framed based on these. Let me first see that exactly if I ask you why this U has come in between your S and V, so I'm just giving you one very simple examples here. I'm just wiping it out from here to make you understand. Let us see here. From the first law of the thermodynamics, we know that du is equal to dq plus dw. Keep in mind that q and the w These are not the thermodynamic properties. These are only the mode of the transfer of the energies. These are the mode of transfer of energy. These are not the types of the energies. Keep this statement in your mind. These are not the types of the energies. These are the mode of transfer of the energies. Exactly here in this case, it is not a thermodynamic property. It is also not a thermodynamic property. If I have to express this du in terms of the thermodynamic property, so I can extend this way. Du is equal to, this is what we find from the second law of the thermodynamics. From the second law of the thermodynamics, you know that ds is equal to dq reversible over here t. In place of dq, I can put up here t into ds, and in place of dw, yani dw is always minus p yani delta v, so plus minus के यहाँ minus, we'll write here pdv. Now this is the expression that I have drawn with the help of some fundamental laws information of the thermodynamics from the expression of the work. This way I have represented this. Now you can understand this internal energy. This is a exact differential. Entropy also in the form of the differential. It is also the differential. This way you can find du, dh, dg and dA. Now let me explain to you why exactly it has come in between here, because its exact differential is related with the exact differential of entropy and the volume. That is why you will have to express this in terms of the differential of entropy and the volumes. Similarly, if you have to express the differential of enthalpy, you will have to express in terms of the differential of entropy and pressure. Likewise, the differential of G can be expressed in terms of the differential of pressure and the differential of temperature. Likewise, the Helmholtz energy in terms of the differential of the temperature and the volume, like this. Now, if I have to achieve this equation directly, how I can obtain this? Let us see here. In between here, directly I am obtaining all the four expressions from here. This is your du. You just write here du. Now it is in between these two yani quantities. One is your entropy and the second one is your V. You write here ds. I'll put here the integral of this with the entropy and how I will just put it, and plus you write here dv. Now the only thing is that I have to put here the integrals. So for that, you remember one thing. You have a diagonal starting from here, the direction of arrow yani towards t. Start the diagonal from here and the direction towards your v. Its integral will be here t. Its integral will be here just in the opposite directions here, that is a t. So you can put here that is a t. Now the question is whether it should be plus or minus. If it is going in the direction of arrow, then the sign taken will be just the positive. Now similarly, integral of v, it is away from the directions and its integral here is p, the sign will be given here the negatives. The plus minus का यहाँ क्या हो जाएगा, that is minus pdv. Let me again emphasize here, if you have to find the integral of this, its integral will be opposite. If it is toward the direction of the arrow, then sign will be taken as a positive. Its integral will be oppositely situated. It is away from the direction, that's why the sign is here the negatives. Is it clear? Similarly, this is the expression. If you even do not know this, you can obtain the expression directly from this Max Born squares. Suppose I want to find here the dH, differential of enthalpy, that is here the dH. dH, this H is in between your entropy and the pressure, so it will be the exact differential of this and this. That is, I am writing here, let us see here, ds, let me put here the sign plus, and this is your dp. Now you have to find out the differentials. Differential of S is just in the opposite directions. Its integral will be taken here t. Similarly, its integral, because your dp, its integral is again in the direction of the arrow. Simply this has become the expressions. dh is equal to tds plus vdp. This is the first expression. This is the second expression. Let me obtain the third expression for the free energies. dg, this is in between p and t. So you can write here the dp plus this is your dt, dp or the dt. Let me again write here, because I am writing here the exact differential of dg. dg can be written as, it is in between p and t. So simply write here dp plus your dt. Now its integral is here v, इसके साथ जो integral आना है, that is here v. It is in the direction of arrow, sign will be here positive. Now its integral is here oppositely situated, as it is going away from the arrow, sign taken will be negative, minus s dt. This is another expressions. This expression also helps a lot in explaining the physical equilibria, under what condition of temperature and pressure the ice changes into water and the water gets frozen into the ice. We can also plot the graphs and based on these expressions. Likewise, it is a dA, this is the Helmholtz energy. It is in between T and V. So let me write here dt plus here dV. Now its integral is here s, away from the arrow, sign will become here negative. V, again its integral is here p, away from the arrow, sign will become here negative. If you know this Born square cycle, you can easily establish this kind of the differential expressions in between basic parameters and the energy potentials. Okay, now the thing is how these expressions are obtained. Very simple. We are seeing here the expression is a T and V. T and V, these are at the corners. P and S at the corners. It means to say these expressions are obtained. In all these expressions, you find that there is no energy potential term involved here. I have just removed these. Only these are here at the corners. So you have to take, just keep in mind, you have to take these two variables and their differential relation has to be maintained with the oppositely situated variables. Similarly, if you take these two, you can establish their relation with the oppositely situated these two. Let me explain how we exactly write these expressions. Suppose S and B I want to write. The partial differentiation of that is your S with respect to that is your V, and what should be a constant? Keep in mind, opposite to this here T, that is add constant and a temperature, at constant and a temperature, it has to be equal to, and now I'll tell you whether the sign will be positive or the negative. It is going in the direction of arrow, that's why the sign has to be here the positive. Okay, differentiation of S with respect to the volume keeping temperature constant with a positive sign will be equal to, now interrelate these two. First you written here S, yani differentiation of S with respect to, that is here V. Now differentiation of P with respect to T, that will be here del P over here del T, and opposite to this is here V at constant volume, that is V. It is in the direction of the arrow, V is in the direction of the arrow, that's why the sign will become in the positive. This is one of the expressions here. It is positive, it is also just the positive. The reverse or the reciprocal of this is also true. If you have written this, it is also quite valid if you can write as dV over ds at constant temperature is equal to its reciprocal dt over dP at constant volume. You can find that these are the kind of the relation that have been presented in the expressions above here. Is it clear? I have expressed this with this. Now let me express relation between this and this. You can take from anywhere. Let me just have here, suppose I am writing here dV over here dt. Now at constant pressure, it is going in the opposite direction of the arrow, sign will become the negative. It will become equal to, now just straight away go here, there is del S over here del P, and opposite to this here T, in the direction of arrow, the sign will become here positive. Even its reverse is also true, del T over del V, the negative sign is equal to del P over here del S at constant temperature, at constant pressures. Is it clear? So if I go for the first question that has been asked, that the incorrect relation is to be found. We have to find the incorrect relations. The first is your T and V. You see here T and V, there is a relation in between this and this. Del T over del V. T का opposite है देखो S. This is going away from the direction, that's why the sign is the negative. This is okay. Now dP over ds, and it is going in the direction of arrow at constant volume. This relation is correct. We have to choose incorrect expressions. Now let's T and P. Del T over del P. T का opposite में देखो S है, sign is the negative. That's okay. Right? T and P. Now you have to go here. That is a del V over the del S, and it is going in the opposite direction. It has to be negative, but here it is written here the positive. It means this is incorrect. और incorrect है तो यही आंसर हो गया, आगे आपको जाने का जरूरत ही नहीं है. इसी तरीके से आप इस क्वेश्चन को भी सिंप्लीफाई कर सकते हैं. तो दिस इज हाउ एग्जैक्टली दिस Max Bone magic square operates. You need to have a bit of the practice of this square. Once, twice you just practice this, you'll be able to solve these kind of the questions. In the next class onward, I'll be explaining how the Maxwell's relations are obtained from this expression, and how exactly two very paramountly important equations of the thermodynamic equations of a state, which will be used in elucidating the internal energy change and the enthalpy change for ideal gas at the condition when the volume is not constant, enthalpy change when the pressure is not constant, and similarly while applying for the van der Waals gases. Hopefully it will be helpful to you. You need to have to practice it a bit, and after twice or thrice you practice this, definitely you'll be able to solve these kind of the questions. Thank you very very much. In the next class onward, I'll be starting with the thermodynamics from the very scratch level, so that it will be highly useful for your competitive examinations. Questions are often asked based on the thermodynamics, and students, due to lack of proper informations, often leave these kind of the questions. Thank you very very much, and have a good night.